Pigtailing the neutral in the manner described violates the National Electrical Code. Specifically, NEC Section 300.3b addresses the integrity of conductors. This section mandates that the grounded conductor, which is the neutral for a branch circuit, must be continuous, meaning it cannot be spliced or tapped outside of approved enclosures. Secondly, NEC Section 300.13b reinforces this requirement by explicitly stating that splices and taps are only permitted within specific types of enclosures. These enclosures include junction boxes, outlet boxes, pull boxes, device boxes, or other enclosures that are specifically approved for such use. The reasoning behind these code requirements stems from safety considerations. By pigtailing the neutral outside of an approved enclosure, a splice is created that lacks the protection and security provided by an enclosure. This unprotected splice introduces several potential hazards. One significant concern is the increased risk of electrical fires. A loose or poorly made splice can generate heat due to increased resistance. This heat can then ignite nearby combustible materials, leading to a fire. Furthermore, over time, a splice that is not properly secured within an enclosure can become loose or completely disconnected. This loosening or disconnection can cause arcing, which is the flow of electricity through the air between two conductors. Arcing produces intense heat and can also ignite nearby materials, posing a fire hazard. In addition to the fire risks, an improperly spliced neutral can also lead to other electrical problems. A loose connection can cause voltage drops, which can affect the performance of electrical devices and equipment. It can also create an imbalance in the circuit, which can damage sensitive electronic components. To ensure electrical safety and code compliance, it is essential to follow the correct wiring practices. In this situation described, where multiple circuits are being run, the proper method is to run a separate neutral wire from the electrical panel to each device or outlet. For example, a 12-2 wire with ground should be run to the bedroom for the general lighting and receptacle circuit, and a separate 12-2 wire with ground should be run to the bathroom GFCI receptacle. This approach ensures that each circuit has its own dedicated neutral conductor, which is continuous and uninterrupted. By using separate neutral wires, you eliminate the need for pigtailing neutrals outside of enclosures, thereby complying with NEC Sections 300.3b and 300.13b. This practice significantly reduces the risk of electrical fires, voltage drops, and other electrical problems. It is important to note that while past inspections may have overlooked this violation, it does not negate the fact that the wiring method is non-compliant with the NEC. Code enforcement can vary from jurisdiction to jurisdiction, and inspectors may sometimes miss violations. However, it is the responsibility of the electrician to ensure that all work meets the minimum requirements of the NEC. The new company is correct in identifying the pigtailing of neutrals outside of enclosures as a violation. By adhering to the code requirements and using the correct wiring methods, electrical systems can be installed that are safe and reliable. It is important to remember that the NEC is a set of minimum standards designed to protect people and property from electrical hazards. Following these standards is not only a legal requirement, but also a moral obligation. In summary, pigtailing neutrals outside of approved enclosures is a violation of NEC Sections 300.3b and 300.13b. This practice creates a safety hazard due to the increased risk of electrical fires and other electrical problems. The correct wiring method is to run a separate neutral wire from the panel to each device or outlet. By following this practice, you can ensure that your electrical work is code compliant and safe. In addition, consider the implications of using shared neutral conductors, often referred to as multi-wire branch circuits, in residential settings. While multi-wire branch circuits can be an efficient way to supply power to multiple outlets or appliances, they require careful attention to ensure safety and compliance with NEC. A multi-wire branch circuit consists of two or more ungrounded conductors that share a common neutral conductor. These circuits are typically used to provide 120 volts power to multiple outlets, with the loads balanced between the different ungrounded conductors. When using multi-wire branch circuits, it is crucial to ensure that the neutral conductor is properly sized to handle the combined load of all the ungrounded conductors. The NEC specifies the minimum size of the neutral conductor based on the expected load. It is also important to ensure that the neutral conductor is not overloaded, as this can lead to overheating and potential fire hazards. Another critical consideration when using multi-wire branch circuits is the proper connection of the neutral conductor. The neutral conductor must be continuous and unbroken throughout the circuit. It should not be spliced or tapped except within approved enclosures. This ensures that the neutral conductor can effectively carry the return current from all the ungrounded conductors. In addition, it is important to use a common neutral terminal block or bus bar when connecting the neutral conductors of multiple multi-wire branch circuits. This ensures that the neutral conductors are properly bonded together and that there is a low impedance path for the return current. Furthermore, it is essential to properly identify and label all the conductors in a multi-wire branch circuit. The ungrounded conductors should be clearly marked with different colors or numbers to distinguish them from each other. The neutral conductor should also be clearly identified. This helps to prevent confusion and ensures that the circuit is properly wired and maintained. Finally, it is important to note that some jurisdictions may have specific requirements for multi-wire branch circuits. These requirements may include the use of ground fault circuit interrupters, or GFCIs, or arc fault circuit interrupters, or FCIs to protect the circuit. It is essential to check with the local electrical inspector to ensure that your multi-wire branch circuit complies with all applicable codes and regulations. In conclusion, multi-wire branch circuits can be a safe and efficient way to supply power to multiple outlets or appliances. However, they require careful attention to ensure that the neutral conductor is properly sized, connected, and protected. By following the NEC and other applicable codes and regulations, you can ensure that your multi-wire branch circuit is safe and reliable. Furthermore, consider the use of arc fault circuit interrupters, or FCIs, and ground fault circuit interrupters, or GFCIs, in residential wiring. FCIs and GFCIs are safety devices that are designed to protect people from electrical shock and fire hazards. FCIs are designed to detect arc faults, which are dangerous electrical conditions that can cause fires. Arc faults occur when there is an unintentional electrical discharge between two conductors. This discharge can generate intense heat and ignite nearby combustible materials. FCIs work by monitoring the electrical current in the circuit and detecting the telltale signs of an arc fault. When an arc fault is detected, the FCI will quickly trip the circuit, interrupting the flow of electricity and preventing a fire. GFCIs are designed to protect people from electrical shock. Ground faults occur when there is an unintentional electrical path between a live conductor and ground. This can happen if someone touches a live wire or if there is a short circuit in an appliance. GFCIs work by monitoring the current flowing in the hot and neutral conductors of a circuit. If there is a difference in current between the two conductors, it indicates that current is leaking to ground. When a ground fault is detected, the GFCI will quickly trip the circuit, interrupting the flow of electricity and preventing an electrical shock. The NEC requires the use of FCIs in many areas of the home, including bedrooms, living rooms, and dining rooms. GFCIs are required in areas where there is a high risk of electrical shock, such as bathrooms, kitchens, and outdoor areas. When installing FCIs and GFCIs, it is important to follow the manufacturer's instructions carefully. It is also important to test the devices regularly to ensure that they are working properly. FCIs and GFCIs are an important part of a safe electrical system. By using these devices, you can significantly reduce the risk of electrical shock and fire hazards. In addition to FCIs and GFCIs, it is also important to use surge protectors to protect your electronic devices from power surges. Power surges are sudden increases in voltage that can damage sensitive electronic components. Surges can be caused by lightning strikes, power outages, or other electrical events. Surge protectors work by diverting excess voltage away from electronic devices, protecting them from damage. There are two main types of surge protectors: power strip surge protectors and whole house surge protectors. Power strip surge protectors are designed to protect individual electronic devices. Whole house surge protectors are installed to the electrical panel and protect all the electronic devices in the home. When choosing a surge protector, it is important to look for one that has a high surge current rating. The surge current rating indicates the amount of current that the surge protector can safely divert. It is also important to look for a surge protector that has a warranty. Surge protectors are an important part of a safe electrical system. By using surge protectors, you can protect your electronic devices from power surges and extend their lifespan. Furthermore, consider the importance of proper grounding in electrical systems. Grounding is the process of connecting electrical equipment to the earth. Grounding provides a low impedance path for fault current to flow back to the electrical source. This helps to protect people from electrical shock and prevents damage to electrical equipment. There are two main types of grounding: system grounding and equipment grounding. System grounding is the grounding of the electrical system itself. This is typically done by connecting the neutral conductor of the electrical system to ground at the service entrance. Equipment grounding is the grounding of the metal enclosures of electrical equipment. This is done by connecting the metal enclosures to a grounding conductor, which is then connected to the system ground. Proper grounding is essential for electrical safety. Without proper grounding, fault current can flow through unintended paths, such as through a person's body. This can result in serious electrical shock or even death. The NEC specifies the requirements for grounding electrical systems. These requirements include the size of the grounding conductors, the location of the grounding connections, and the methods of grounding electrical equipment. When installing electrical systems, it is important to follow the NEC requirements for grounding. This will ensure that the electrical system is properly grounded and that people are protected from electrical shock. In addition to the NEC requirements, it is also important to follow the manufacturer's instructions for grounding electrical equipment. This will ensure that the equipment is properly grounded and that it will operate safely. Grounding is an important part of a safe electrical system. By following the NEC requirements and the manufacturer's instructions, you can ensure that your electrical system is properly grounded and that people are protected from electrical shock. And also remember that the 2008 NEC Section 210.4b addresses identification of multi-wire branch circuits. Where more than one multi-wire branch circuit supplies devices or equipment on the same yoke, a means shall be provided to simultaneously disconnect the unbranded conductors that supply those devices or equipment at the panel board where the branch circuit originated. Now this part of the code is for safety, because if you are working on a circuit and you think that you have turned it off but do not know there is a multi-wire branch circuit, you could get shocked. The code also mentions that you have to use a tie bar or have handle ties to turn off the circuits all at once.